Hi, this is Stu Schwartz from MasterMathMentor.com. This is super free response practice AB question number 4. Super free response questions are similar to the typical free response questions in past AP exams. But instead of having the usual 3 or 4 subparts, these will have a great many more. It allows us to use the problem setup as a source of many inquiries that can be taken and allows us to do an in-depth study of the situation. Because of that, many calculus concepts are tested and some reiterated. Doing these will take more than the usual 15 minutes, but by tackling all subparts, you will know what topics you need to emphasize as you prepare for the AP exam. It is recommended that you go to the MasterMathMentor website and download the PDF with the actual problem and subparts. If you don't have a printer available, use a piece of paper for parts A, B, C, etc. This video will just show you the solutions, although you can fast forward at times to bypass the solutions and just show the problems. Number 4 reads, the continuous function f is defined on the closed interval x between -6 and 6 inclusive. The figure shows a portion of the graph of f consisting of 3 line segments, a semicircle centered at the point 2, 2, and a quarter circle centered at the point -1, 2. Before we start on this problem, realize that this question is from a class of AP free response questions where students are given a graph of a function and then asked all sorts of questions about the function or related functions. Vital to the question is to understand what is actually given. There are 2 situations that crop up regularly. Given is usually f of x or f prime of x, although it is possible to be given f double prime of x as well. It usually is identified in the stem of the question and under the graph itself. Students must focus on this information as how to do the problems differ radically based upon that, making such an AP question an all or nothing affair in terms of points achieved by students. In the left-hand picture, we are given a graph of f. So we can see that there is value on the x-axis at x is equal to a, and the corresponding point on the graph in red is the point a, f of a. Therefore, the area shaded in blue would simply be the integral from 0 to a of f of x dx. And if you are asked to find the tangent line to f at x is equal to a, we would use our point slope formula, which would be y minus f of a equals f prime of a times the quantity x minus a. We know f of a, but we would need to find the derivative of f prime of a. And we would need at that point to actually know what the function is, or possibly if we were given a set of points, we could approximate the derivative. However, in the picture of the right, suppose that the blue curve represents the graph of f prime. So at x is equal to a, our red point is the point a, f prime of a. Therefore, the blue shaded area would be the integral from 0 to a of f prime of x dx. And we know that the integral of f prime is simply f. So this would be f of x evaluated from 0 to a, and therefore the area in terms of f would be f of a minus f of 0. If, again, we were asked to find the tangent line to f at x is equal to a, we would use our point slope formula, y minus f of a equals f prime of a times the quantity x minus a. We are given f prime of a, as we have the point a f prime of a. We would use the area formula above to realize that f of a is equal to f of 0 plus the integral from 0 to a of f prime of x dx, or f of a is equal to f of 0 plus the area under that curve. So both problems are radically different based upon whether our graph is f or f prime. So be sure to identify that as you do problems of this nature. In this type of problem, where the graph of f is comprised of line segments and parts of circles, where area is generally easy to find, no calculator is permitted. And in reality, a calculator would not be of much help, as the functions are not explicitly given algebraically. Part A asks, what is the minimum number of locations where f has a horizontal tangent line? And we need an explanation. First, realize that it asks for the minimum number of locations because the f is defined on the interval -6 to 6, and we are only seeing the section of the curve from -4 to 6. So we really don't know what is happening between -6 and -4. F having a horizontal tangent line is interpreted as f prime of x is equal to 0. This only occurs at x is equal to 2, as f prime of 2 is equal to 0. The other candidates seem to be at x is equal to -2, x is equal to -1, and x is equal to 4. But they are either corners or cusp points, and therefore at those locations f prime of x does not exist. 2 points are allocated for this problem, one for the answer of x is equal to 2, and 1 point for the explanation. Part B asks for the minimum number of locations where f has a vertical tangent line, and again needs an explanation. And as we saw in A, we have to ask for the minimum number of locations because we do not know what's happening with f between -6 and -4. The solution to B is also 1, and this occurs at x is equal to 0, as the limit as x approaches 0 from the left of f prime of x is the same as the limit as x approaches 0 from the right of f prime of x, which is infinity. At x is equal to -2, x equals -1, and x is equal to 4, the left and right hand limits are not infinite, so there is no vertical tangent. As in part A, 1 point for the numerical answer of x is equal to 0, and 1 point for the explanation of why there is a vertical tangent at x equals 0. There does not have to be any discussion about why there are no vertical tangents at x is equal to -2, -1, and 4. In C, we're told that g of x is equal to f prime of x times f double prime of x, where x is a number from -4 to 4 inclusive. And we would like to know the values of x for which g of x is greater than 0. And we also need to justify our answer. G of x is positive only when f prime of x and f double prime of x have the same signs. They both must be positive or they both must be negative. F prime of x is greater than 0 on the interval -2 to 0 and 0 to 2, while f prime of x is negative on the intervals -4 to -2 and 2 to 6. Note that we don't make any statement about what is happening at x is equal to -2 and x is equal to -1 and x is equal to 0 as well as x is equal to 4. The f prime will be not defined at those values, but it will not affect our answer. Lines have no concavity, and concavity has to do with f double prime of x. So therefore, f double prime of x is equal to 0 on -4 to -2, -2 to -1, and 4 to 6. And therefore, f double prime of x is positive on the interval -1 to 0, as it is concave up in that section, and f double prime of x is negative on the interval 0 to 4 as it is concave down. So g prime of x has to be greater than 0 only on the intervals -1 to 0 and 2 to 4. For points, we get 1 point for the point -1, 0, 1 point for the point 2, 4, and 1 point for the justification. D reads, find the value of the integral from 0 to 4 of f of x dx. This is about as straightforward as we can get. We are being asked to find the area under the f curve from 0 to 4. This represents a semicircle sitting on top of a rectangle. The rectangle has base 4, height 2, so its area is 8. And the semicircle has area 1/2 pi radius squared, and the radius is 2, so 1/2 times 4 pi. And the answer is 8 plus 2 pi. For grading, 2 points, 1 point for the 8, 1 point for the 4 pi. In E, we are asked that if the integral from -6 to 0 of f of x dx is equal to 2 plus pi over 4, we would like to find the integral from -6 to -4 of f of x dx. As noted before, the graph of f was defined on -4 to 6. However, the domain of f was given as -6 to 6. So we know very little about what is occurring on the graph between -6 and -4. However, we can utilize the fact that the integral from -6 to 0 of f of x dx is equal to the integral from -6 to -4 of f of x dx plus the integral from -4 to 0 of f of x dx. Therefore, the integral from -6 to -4 of f of x dx is equal to the integral from -6 to 0 of f of x dx minus the integral from -4 to 0 of f of x dx. So the integral from -6 to -4 of f of x dx is equal to our given 2 plus pi over 4 minus that total area under the curve from -4 to 0. When we look at that, we realize that between -4 and -2, we have a triangle whose area is 1, and being below the x-axis, we use -1. We then have two triangles that cancel each other out between -2 and -1, -1/2 plus 1/2. And then we have the area under the quarter circle, which is 1 plus 1 minus pi over 4. So the integral from -6 to -4 of f of x dx is 2 plus pi over 4 minus quantity, -1 minus 1/2 plus 1/2 plus 1 plus 1 minus pi over 4. And therefore our final answer is 1 plus pi over 2. This is a 3-point problem. 1 point for the formula for the integral from -6 to -4 of f of x dx being the integral from -6 to 0 of f of x dx minus the integral from -4 to 0 of f of x dx. 1 point for correctly computing the integral from -4 to 0 of f of x dx, and then 1 point for the answer. In f, we are asked to find the integral from -2 to -1 of 4f prime of x minus 3 dx. To solve this, we utilize the fact that the integral from -2 to -1 of 4f prime of x minus 3 dx can be split into two integrals. For integral from -2 to -1 of f prime of x dx minus the integral from -2 to -1 of 3 dx. Next, we use the fact that the integral of f prime of x dx is f of x. And we get 4 f of x evaluated from -2 to -1 minus 3x evaluated from -2 to -1. This gives 4 quantity f of -1 minus f of -2 minus quantity -3 plus 6. F of -1 is 1. F of -2 is -1. So we get 4 quantity 1 plus 1 minus 3, or 8 minus 3, or 5. In terms of points, 1 point is allocated for realizing that the integral of f prime of x dx is simply f of x. 1 point for the integration of each piece, and then 1 point for the final answer. Problems G and H go hand in hand with each other. G reads, let capital F of x be defined on the interval -4 to 6, and capital F of x equals capital F of 0 plus the integral from 0 to x of f of t dt. We would like to express f of 6 minus f of 4 as a definite integral and show the reasoning. This looks difficult, but is actually fairly straightforward. We first plug in our 6 to our formula and get f of 6 equals f of 0 plus the integral from 0 to 6 of f of t dt. We plug in -4 and we get f of -4 equals f of 0 plus the integral from 0 to -4 of f of t dt. Looking at f of 6 minus f of 4, we get f of 0 plus the integral from 0 to 6 of f of t dt minus quantity f of 0 plus the integral from 0 to -4 of f of t dt. The f of zeros cancel out, and therefore we get the integral from 0 to 6 of f of t dt. And we can now write the second integral as plus the integral from -4 to 0 of f of t dt, and that we know is simply the integral from -4 to 6 of f of t dt. Realize that the answer could also be expressed as the integral from -4 to 6 of f of x dx. The variable does not matter. For grading, you get 1 point for expanding capital F of 6 and capital F of -4, and then 1 point for expressing your answer as a definite integral of little f. In H, we are asked to use the answer we just got in G to find the value of f of 6 minus f of -4. As we just showed, f of 6 minus capital F of -4 is the integral from -4 to 6 of little f of t dt, which is the total accumulated area under the curve. Starting at -4, we go to -2, and our first area is -1. We then have two triangles, one with an area of -1/4 and then an area of 1/4. From -1 to 0, we have our quarter circle under a square, and we get 1 plus 1 minus 1/4. Next, we have the semicircle under the rectangle, and that will be 8 plus 2 pi. And then finally, we have a right triangle whose area is 2. Adding it all up, we get 11 plus 7 pi over 4. For points, 1 point is allocated for the area under the lines, which is 7, and 1 point is allocated for the area under the circles, which is 7 pi over 4. Part I asks for intervals where capital F is increasing and a justification is necessary. Whenever you see the words F is increasing, that means you must take the derivative of F. So capital F prime of X is the derivative of capital F of 0 plus the integral from 0 to x of f of t dt. And we know that the derivative of a constant is 0, and the derivative of the accumulation function is simply f of x. So capital F prime of x is equal to little f of x. And you have to remember that you are looking at little f of x. So we're interested in where little f of x is greater than 0, and that is on the interval -3/2 to 6. So in terms of grading, 1 point for the interval. It makes no difference whether parentheses are used or brackets are used. And 1 point for the reasoning. J asks, if capital F of 0 is equal to 2, then find the maximum value of capital F. Since f is increasing on -3/2 to 6, it is also decreasing on -4 to -3/2, meaning that the maximum value of f must occur at one of the endpoints, capital F of 6 or capital F of -4. F of 6 is f of 0 plus the integral from 0 to 6 of f of x dx, and that becomes 2 plus the area under the curve, 10 plus 2 pi, and we get 12 plus 2 pi. F of -4 is f of 0 plus the integral from 0 to -4 of f of x dx, and it is probably easier to express this as 2 minus the integral from -4 to 0 of f of x dx, and this becomes 2 minus the quantity, -1 plus 1 minus pi over 4, and we get 2 plus pi over 4. So the maximum value of f must be 12 plus 2 pi. For grading, we get 1 point for testing one endpoint, 1 point for testing the other endpoint, and 1 point for the actual answer. In question K, you are asked for what values of x does f have an inflection point, and to explain the reasoning. To determine inflection points, we have to look at concavity. So we must look at f double prime of x. Since capital F prime of x is equal to small f of x, f double prime of x capital is equal to small f prime of x. So we make a sign chart for f double prime of x, which is the same as f prime of x. Between -4 and -2, it is negative. At -2, it is infinite. Between -2 and -1, it is positive, and at -1, it is infinite. Between -1 and 0, it is positive, and at 0, it is infinite. Between 0 and 2, it is positive. At 2, it is 0. Between 2 and 6, it is negative, but at 4, it is infinite. So since capital F double prime of x switches signs at x is equal to -2 and x is equal to 2, then capital F has inflection points at those locations. Note that although at x is equal to -2, f double prime of -2 is infinite, this does not change the fact that there is an inflection point there. Capital F of -2 represents the accumulated area from 0 to -2, and that number exists, which means that there could easily be an inflection point there, even though the second derivative is infinite. For grading, there is 1 point for stating that capital F double prime of x is equal to f prime of x. 1 point for the two locations, x is equal to -2 and x is equal to 0, and 1 point for the actual reasoning. Note that you do not get the reasoning point if only the sign chart is used. There must be an explanation that f double prime is switching signs. Question L asks, what is the numerical difference between the average rate of change of capital F on -4 to 6 and the average value of little f on the interval -4 to 6, and explain. In a way, this is kind of a trick question because these are the same entities, so the difference is 0. Students get these terms confused all the time. The average rate of change of capital F over the interval -4 to 6 is capital F of 6 minus capital F of -4 over 6 minus -4, which is capital F of 6 minus capital F of -4 over 10. The average value of little f would be the integral from -4 to 6 of f of x dx over 6 minus -4. And we know that the integral of little f is capital F. So that is capital F of x evaluated from -4 to 6, which is f of 6 minus f of -4 all over 10. 2 points for this problem. 1 point for the answer of 0, and 1 point for the explanation showing that they are the same calculations. In M, you are asked to find the equation of the tangent line to capital F at x is equal to 2. Whenever you are asked to find the equation of a tangent line, you need two pieces of information to use the point-slope formula. We need the value of the function at x is equal to 2 and the value of the derivative of the function at x is equal to 2, meaning we need capital F of 2 and capital F prime of 2. Capital F of 2 is, by definition, f of 0 plus the integral from 0 to 2 of f of x dx. F of 0 is 2, and the integral from 0 to 2 of small f of x dx is 4 plus pi. And therefore, the value of the function is 6 plus pi. We need the value of f prime of 2, which is little f of 2, as we've seen before. And little f of 2 is 4. 3 points for this problem. 1 point for finding f of 2, 1 point for finding capital F prime of 2, and then 1 point for the equation. So our tangent line equation is y minus quantity 6 plus pi is equal to 4 quantity x minus 2, or y is equal to 4x minus 2 plus pi. In N, we want the limit as x approaches 2 of capital F of 3x minus capital F of 2x minus x over tangent pi x. First step in a limit problem is to plug in, and we get capital F of 6 minus capital F of 4 minus 2 over tangent of 2 pi. We know that capital F of 6 minus capital F of 4 is the integral from 4 to 6 of little f of x dx minus 2 over the tangent of 2 pi, which is 0. The integral from 4 to 6 of f of x dx is simply the area of the right triangle, and that is 2. Minus 2 over 0, and we get 0 over 0. So we will now use L'Hopital's rule, and we get the limit as x approaches 2 of the derivative of f of 3x is 3f prime of 3x minus 2f prime of 2x minus 1 over the derivative of tangent of pi x is secant squared of pi x times pi. And when we plug in 2, we get 3f prime of 6 minus 2f prime of 4 minus 1 over pi secant squared of 2 pi. That gives us 3 little f of 6 minus 2 little f of 4 minus 1 over pi, as secant squared of 2 pi is 1. F of 6 is 0. F of 4 is 2. So we get 3 times 0 minus 2 times 2 minus 1 over pi, and our answer is negative 5 over pi. 3 points for this problem, 1 point for getting 0 over 0, then 1 point for the correct use of L'Hopital's rule in terms of the formula, and then 1 point for actually applying L'Hopital's rule and getting the correct answer. Question O asks, if applicable, apply Rolle's theorem to f on the closed interval negative 4 to 6. If it is not applicable, explain. Rolle's theorem states that if f of A is equal to f of B, then there must be some location C between A and B such that f prime of C is equal to 0. And in this problem, yes, f of negative 4 is equal to f of 6, which is equal to 0. However, there are certain conditions that must be met in order for Rolle's theorem to hold. One of them is that f must be continuous on the interval, and it is. But f must also be differentiable on the interval, and there are multiple locations between negative 4 and 6 where f is not differentiable. So Rolle's theorem is not applicable in this case. So 2 points here, 1 for the conclusion that it is not applicable and 1 point for the reasoning. P reads, on the graph of little f, the section between x is equal to 2 and x is equal to 4 is divided into intervals, 2 to 2.25, 2.25 to 2.5, 2.5 to 2.75, 2.75 to 3, 3 to 3.25, 3 to 3.25 to 3.5, 3.5 to 3.75, and 3.75 to 4. We would like to know for which of these intervals does the conclusion for the mean value theorem hold for capital F of x, and we'd like to show the work that leads to the conclusion. Capital F represents the accumulated area under the graph of little f. Capital F is certainly continuous on the interval 2 to 4 and differentiable on the open interval 2 to 4. Therefore, the mean value theorem says that capital F prime of C must equal f of 4 minus f of 2 over 4 minus 2. However, capital F of 4 minus capital F of 2 is the integral from 2 to 4 of f of x dx, and this simply is the area under the curve, little f from 2 to 4. That is 4 plus pi. So capital F prime of C is equal to 4 plus pi over 2, which is approximately 7.14 over 2, which is 3.57. However, realize that capital F prime of C is the same as little f of C. So we're interested in what interval is f of C equal to 3.57. And we can see by the graph that C must be a number between 3 and 3.25. So 1 point for continuity and differentiability statement, 1 point for the correct use of the mean value theorem, and then 1 point for the interval 3 to 3.25. There are 40 points available for this question. There is no exact formula for what number of points will constitute a 5, 4, 3, 2, or 1 on the AP exam. However, these percentages are what have been used in the past based upon exams released by the College Board. While you can extrapolate for just this question, realize that this question only tests a limited number of AP topics. So it is recommended that you do a number of the super free response questions in this series. Then combine your results, total your points, and then use these percentages to get a feel for how you will do in the AP exam. And more importantly, what concepts you need to strengthen in order to improve your score.